So now we begin with parametric equations for surfaces. Okay, so where is this coming from? Previously, we described a one-dimensional curve using parametric equations. So imagine that curve existed in 3 dimensions. So you could describe it in 3 coordinates. And of course, we use X, Y, Z coordinates typically. So where the graph is differentiable, you could zoom in on a point of the graph and see a straight line. And then that always tells you that the graph can be expressed as a function of one variable, and we typically use the parameter t. And then the formula for the curve is written like this. R of t, curve C is R of t equals X of t, comma Y of t, comma Z of t. Okay, so that was what we had done before. Now we kick it up a notch, and we really kick it up a dimension. So what do we got? Okay, so now we're going to describe a 2-dimensional surface using parametric equations. Now, a 2-dimensional surface could be graphed in any number of dimensions. We're going to stick with just talking about what we see in 3 dimensions. So therefore, we'll look at surfaces that can be described using 3 coordinates, x, y, z. Now, of course, if we have a 2-dimensional surface, and if derivatives exist and you zoom in, then it looks like a plane. Of course, we've talked about this before. This is the tangent plane. And it resembles the R2 plane. And to describe this plane, of course, you would need 2 variables to describe it. Now, to describe our surface, we're typically going to use the parameters u and v. So the formula for the surface S is written like this. So we use R, and now it's going to be R of u and v. And so the 3 coordinates are each functions of those 2 parameters. So it's x of u of v, comma y of u of v, comma z of u and v. So for this function R, which describes the surface, the input is a 2-dimensional point, which we're going to write in uv. And then the output is a 3-dimensional point, which we're going to think of as existing in our traditional or typical XYZ space. So as a result of all that, the surface itself is 2-dimensional, but we represent the graph of the surface in 3 dimensions or 3 coordinates. Yeah. So actually, let's present the graph of what's going on here. Okay. So this is sort of the picture of what's going on. So notice that it's helpful to think about the parameters that we're going to use as one specific space. This was less of a problem with the one-dimensional curves because it's just like, oh, the parameter t, sure, that makes sense. But now we've got parameters u and v. So it's going to be more helpful to think of it as its own space. That's what we see on the left. And then that's sort of like a region in R2. It's a region in a plane. Now the function R takes a particular point into a 3-dimensional coordinate space. And that's what you see graphed on the right. And so one particular point, uv, the function R takes to some point x, y, z. And also, it's important to be able to think about that entire region, on the left, the entire 2-dimensional region gets taken to, by the function R, a surface on the right. Now, the surface itself is 2-dimensional, but because it kind of bends and moves and, the way parametric curves can do, we need 3 coordinates or 3 dimensions in order to graph it. So that's the idea. Let's take a look at a specific equation and a specific example. So here's the formula. Graph the surface R equals 2 cos u, comma, 2 sine u, comma, v. So here's the graph rendered in 2 slightly different ways. So now let's compare this with the old way that we would graph stuff. So previously for the surface z equals f of xy, one way to think about it would be to make traces. So you would take everything, so x constant or y constant, and then you have like z as a function of x or z as a function of y. And that would create a sort of coordinate grid on the surface itself if you thought about those traces. Okay, so now we're gonna talk about how do we make a coordinate grid for parameterized surfaces. So for this, we're gonna make the parameters u constant and then v constant. And that's gonna give us those lines. So on the left, you'll see the surface just graphed as the surface, but on the right, you'll see the surface graphed with those traces. Now, in particular, note that slicing it using a constant x or constant y, which of course those are planes themselves, slicing it in that way does not work, since this is a parametric. This is written parametrically, and z is not necessarily a function of x, and z is not necessarily a function of y when you hold the other variable constant. So let's talk about what happens in this particular one. So in this example, if you just take v fixed, notice that v in the formula only appears in the third coordinate. So basically you're taking the height fixed, and then you have what? 2 cos u and 2 sin u. So as u varies, that's just the formula for a circle. So for constant v, the trace that you get is a circle of radius 2 at different heights. And so notice that that gives you those particular traces on the surface. Next, what if u is fixed? So if u is fixed, you can think of it as being like at a specific point on that circle, and then as v varies, basically the height changes. And so that gives you the vertical lines. And so that will give you those lines. And so these are, previously we've called them traces. Typically for parameterized surfaces, they're called grid lines. And of course, as we know and as we see again here, parametric equations are more general and more versatile than a function equation. So let's take a look at, so hopefully that example was a little generalized because z is clearly not a function of x and y when you finally graph it. But hopefully relatively simple, so you could still sort of catch on to what the grid lines were. So now we're definitely going to kick it up a notch. So here is a picture of fusilli bucati. So this pasta is in the shape of a corkscrew, but it's hollow on the inside. With parametric equations, we can write the formula for this tasty pasta. And there's the formula. And there is the actual graph just based on that equation. So let's break this down and see what this formula is telling us in terms of the grid lines. Okay. So looking at the formula, if v, so we got u plus cos v, comma 2 plus sine v times cos u, comma 2 plus sine v times sine u, and then plus 3. So the plus 3 there in the final coordinate just sort of lifts the graph up. So we can skip that for a moment as we think about it. So for constant v, what happens as u changes? As u increases, the x-coordinate is getting bigger. There's just the u plus in the x-coordinate. But then also, in the second, in the y and z coordinates, you've got a cos u and a sine u. So you're increasing in the x direction while you're basically making a circle in the YZ plane or YZ orientation. Okay. So if you think about that happening, then it's sort of making these, it's basically making like a corkscrew for constant V as U increases. And that gives you those sort of corkscrew wrapping around the Fusili Bacatti, wrapping around the graph grid lines that you see on the bottom. That's first of all. Second of all, if U is constant, as V increases, what's happening? Well, Y and Z will both oscillate like a sine curve because they both have a sine V in them. But the X coordinate has a cosine in it. So it's going to oscillate like a cosine curve. So you're going to get these loops. Now the loops, because of the other terms, the loops are kind of complicated, but it gives you these sort of oscillating loops. And that gives you those other grid lines that you can see on the graph on the bottom. Those are a little more complicated, but just at least you can get the idea that it's sort of oscillating back and forth and going in some kind of twisted loop. Okay. So that is an introduction into what does it mean to have a parametric equation, to use a parametric equation to draw a surface. So you're getting, at the end of the day, a two-dimensional shape, even though we're going to graph it, in our case, in 3 dimensions, or 3 coordinates. So now we'll talk about the special case. So a special case that you've actually seen previously in your first year of calculus, which is surfaces of revolution. So, so you've talked about taking a graph y equals f of x and rotating it around the x-axis. You may have done other rotations as well, perhaps revolving it around the y-axis or revolving it around some other particular line. We're going to focus on revolving around the y-axis, around the x-axis as usual. Okay, so when you make that surface of revolution, cross sections of that surface are circles. So what that means is that when x is constant, then the circle, what you get a circle in the YZ plane. And for that circle, the radius comes from the value of the function f of x, and the center is the x-axis, where you've got 0, 0. So in the YZ plane, the parametric equation of that circle is given on the bottom here. YZ equals just r cos theta, r sine theta, where r was the value of the function. So it's just f of x times cos theta, comma f of x sine theta. Now that's just for the circle for a fixed x. So now, reintroduce the x coordinate to get the whole formula. So you can complete the parameterization anyway. Typically, we just let x equal t. So therefore, your formula is now r equals xyz, which equals t, comma, f of t times cos theta, comma, f of t sine theta. So note that doing it like this, we intuitively, or we naturally use t and theta as our 2 parameters. We'll typically use u and v, but we don't have to. In this case, it makes sense to think of one of the parameters as theta, and it's perfectly fine to just go ahead and write it that way. Okay. So let's look at a specific example of how this works. So let's say we've got y equals 4 minus x squared, and we take only the y positive part of that, and then we rotate it around the x-axis. Let's find the parametric equation for that surface. So the first thing we want to do is notice that if y is positive, that immediately tells you that x goes from -2 to 2. That you've solved for something like that before, but just to make it clear, solve for where y equals 0, and you just get 2 plus x, 2 minus x, so x is plus minus 2, and those are the endpoints. So x is between them. Okay. And of course, there's an upside down parabola. Okay, so x goes from -2 to 2. And now we can make our parameterization. So the formula for this surface is going to be r equals t, comma, 4 minus t squared cos theta, comma, 4 minus t squared times sine theta. And of course, a full revolution means theta is going to go from 0 to 2 pi. And t, since we let x equal to t will just go from -2 to 2. And what that gives you is this graph right here. So if you notice, these sort of arches over here, there's an arch on the top, and that represents kind of your original graph. So think that's sort of like your theta equals 0 trace or grid line. And then, of course, at different values of theta, that gets sort of that's at a different angle, so that gets wrapped around. And then similarly, if you take t to be fixed, then that's like a fixed x value. And then as theta varies, that just wraps around and you make a circle. So you get all these circles of different radii at different x values. And that's how we can describe it. So put it all together, and what do we have? We talked about parametric equations for surfaces. So you get a surface which itself is two-dimensional, even though we're representing it in using 3 coordinates. And we also talked about we just talked about here the special case where it comes from where the surface is specifically a surface of revolution. And we'll just restrict ourselves to the case of revolution around the x-axis.